Let's see if we can't try this the right way. What's the point of electromagnetism? Anyone will be inclined to answer that the entire point is contained in the immense technological impact it's had. And it's hard to really disagree with that, honestly, because the impact is immeasurable. But electromagnetism independently represents a coherent body of thought that mostly came into maturity somewhere in the middle of the 1800s. And it has a much more interesting significance, and that is a philosophical significance. You see, electromagnetism in part was intended to address a serious philosophical crisis that was set off by Sir Isaac Newton after he formulated the universal law of gravitation. It's a very well-known crisis among academic circles, but not so much among conventional physicists and much less among engineers. You see, the crisis had to do with a couple of things. So the universal law of gravitation, right? Newton is quite correctly associated with this more than anything else in the common imagination, the public's imagination. But one of the ideas embodied in the universal law of gravitation is that the force of attraction, gravitational attraction felt between any pair of objects in the universe depends on the masses of the objects, meaning the weights in a sense, and besides that, the distance between them. All right, but one of the consequences of this simple fact is that the moment the distance between the objects changes, like say one object moves further away, well, the force of attraction between them changes quite instantly. Now, this is almost normal, except for one thing. There is no delay between the movement of the object and the change in the force of attraction. It takes a little careful reflection to see what this really means and why it was confusing and why it set off a big moral and philosophical dilemma among people of the time, of Newton's own time, and no less than Newton himself. The reason it's confusing, it was confusing to people is, say you have two people standing. Now this is quite an abstract scenario, but say you have two people standing in a forest and they are quite far away from one another. There are lots of bushes and trees or something between them, so they really can't see each other. But they're in a forest nonetheless, and each of them are carrying a little device which would measure the gravitational force exerted on them due to the other. All right, let's call these two people A and B. According to Newton's universal law of gravitation, the moment that A moves somewhere else so that he or she is at a slightly larger distance from B, B gets notified of it. Think about this a moment. The moment he or she changes position, B gets notified. Is this similar to passing signals via walkie-talkie? Not really, because there is no signal being passed. There is no delay between A moving out of his or her position and B being notified. This means that in some very strange way, A and B are connected, physically connected, logically connected. They, even though we have an instinct to regard A and B as basically independent of each other, they aren't. And the moment A's position changes, B experiences something. In fact, B's position may also change because of the force of attraction towards A, gravitational attraction. A little further reflection will make it very clear why this was confusing and at the very least unintuitive. So it is mainly the British philosophers like David Hume and John Locke who pounced on this fact, and he tried to use it to demonstrate the idea that the world is full of occult qualities, strangeness. We don't know that the world does not need to conform to our intuitions. Our intuitive picture of things just does not need to be true, and perhaps there will always be phenomena for which there is no intuitive explanation. And basically, they're saying the world is a scary place. We don't know what's out there. We don't know what creatures are hiding out there. But Faraday and Maxwell came along, and about 100 years after Newton passed away, and managed to resolve this. It's important to note that Newton himself felt this crisis very deeply. He wrote a letter to his friend, the dean or something of Cambridge, and said that the law is so strange in this particular aspect that no one in their right mind would accept it. No one with an ounce of sense would accept this law as it is. Someone will come along and modify it. And that someone was this Faraday and Maxwell. Although they were not so interested in gravity, they were more interested in electricity and magnetism. But basically, they came up with a hint at a solution. The proposal by Maxwell was, we do not need to, let's stop talking altogether of objects interacting with one another, which is the old picture of Newton. Instead, let us imagine that the way in which any object exerts a force on another is by letting out a field, that is, letting out an influence in its immediate environment. And any object that manages to fall within that region of influence gets affected. In other words, gets influenced. This might seem like just a slight modification of Newton's original picture, but it isn't. Closer reflection and the more nuanced details provided by James Clerk Maxwell to Faraday's idea actually ended up resolving that philosophical crisis and removing the so-called occult qualities which Newton's law of gravitation seemed to conceal. And it was decided later on that for in any object exerting forces on another object, this was the scheme we'd have to follow. That is, a field would be let out in space, and perhaps an object comes into the region of that field. And in that sense, the two objects really are independent. If we say that there is a delay in the time that it takes for the field to affect the second object, then there will also be a delay between the second object being notified about a change in position of the first object. I don't know if that's entirely clear or logical to you, but a little reflection will hopefully prove it to be clear and logical. There was also another issue with Newton's universal law of gravitation, and that was the formula you might have learned in school. It's a nice and simple enough formula, but Newton could not explain why it looked like that. He could not make it simpler than he had already made it. And here Maxwell came along and made it simpler using the field picture of Michael Faraday. Now, the introduction of the field was a major revolution in physics and in general thought, because it involved getting rid of Newton's old suggestion that we describe everything in terms of objects which are made up of so-called material points. And these material points interact with other material points through various forces. And most of those forces are contact forces, push and pull, etc. And the only non-contact force he concerned himself with was gravitation. But the field idea was much more intuitive. It resolved the difficulties of the old Newtonian program. And it took a long time for scientists to come around to the notion of the field. Even though it's very intuitive to children, scientists who were set in their ways were not really ready to accept it as established science, so to speak. It was, in fact, many decades before it was even taught in schools. And among the first generation of European students who learned it in school was a precocious young student named Albert Einstein. He was deeply moved by the idea of the field that Faraday had introduced into physics. He even said that it is impossible for someone like him to measure the influence of Faraday's ideas because they were so fundamental to him. Einstein did a couple of great things with these ideas. First of all, he tied up all the loose ends that Maxwell and Faraday had left behind. Maxwell and Faraday were not able to explain how light seems to have the same speed, whether you're moving towards it or away from it. And Einstein managed to clear those problems away with his special theory of relativity. And 10 years after he established a special theory of relativity, he fulfilled Newton's dream of someone coming along and replacing the universal law of gravitation with a better law in which objects don't interact like this at a distance instantaneously. Einstein's model for gravitation is what we today call the theory of general relativity. It was a replacement for Newton's universal law of gravitation, and it managed to establish a kind of signal that passes between objects when they exert a gravitational force on one another after they change positions, etc., etc., etc. The recent experiments with the so-called gravitational waves has given Einstein's theory an even deeper power and substance in its resolution of the old problems set off by Newton. So that's my answer to the question, what's the point of electromagnetism? It's hard to answer such a question completely, or even to a sufficient, to an acceptable degree, but there you are. If you want to learn more about the subtleties of the question and of electromagnetism, head on down to the Centaur Courses and we'll have a chat. See you.